Now in this lecture video we're going to be looking at how to perform approximate hypothesis tests about a population median. Now in the development that we've looked at so far, we have looked at basically three types of hypothesis test about the population median. We've looked at a left-tailed test, a right-tailed test, and a two-tailed test. Much as we did in looking at hypothesis tests about means, population proportions, and population variances. Now in the procedure that we've looked at for testing hypotheses about a population median, we've used a test statistic that we've called EXST. And EXST, you'll remember, is the number of observations in the sample that are greater than the hypothesized value of the median. In order to use EXST in a hypothesis test, we have to know something about its sampling distribution under the conditions of the null hypothesis. Now, if the null hypothesis is true, and in particular if the boundary condition of the null hypothesis is true, then as we've discussed and shown and utilized, the sampling distribution has a binomial distribution with n equal to the sample size, and p, the success probability, equal to 0.5. And so that is the appropriate reference distribution in performing these tests, and that's the distribution from which we determine appropriate critical points depending on the significance level that we want to use. And it's also the distribution that we use to calculate the p-value of a test. Now, in order to determine these critical points and in order to calculate p-values, we have to be able to evaluate the CDF, the cumulative distribution function of the binomial distribution with n trials and success probability p equal to 0.5. We have to be able to evaluate that CDF in order to do those things, and that can be fairly tedious and computationally intensive to do. If we've got a calculator like the TI-84 or the TI-36X Pro that has the binomial distribution built in, then it's not too difficult to get values for the CDF for that distribution. But if we don't have such a calculator, or if we don't have computer software that calculates the binomial CDF, then it can be quite tedious and difficult to do those calculations. One way to get around this problem is to look for some kind of an approximation to the sampling distribution of EXST. In other words, try to find an approximation to the binomial distribution with n trials and success probability p equal to 0.5. And so that is the topic of this lecture, perhaps a few more, on how to do this, how to approximate the sampling distribution of EXST under the conditions of the null hypothesis, so that we can perform these hypothesis tests more readily without having to do all the calculations involved with the binomial CDF. Now, the one thing we need to keep in mind that the approach that we're going to be looking at in this lecture, it's an approximation. That approximation, it may be a good approximation, and it may not be a good approximation. It's going to depend on the sample size, as these things typically do. In general, the approximation will improve as the sample size increases, but keep in mind that for small samples, which is the context in which nonparametric statistics are often used, this approximation may not be that great. So we just need to keep that in mind. With that in mind, what we're going to be doing is invoking the central limit theorem and using what we've learned in our prerequisite statistics class about the normal approximation to the binomial distribution. Since the true sampling distribution of EXST is the binomial, and under the conditions of the null hypothesis, it's the binomial distribution with a success probability of 0.5, it stands to reason that if the sample size, n, is large, then we ought to be able to approximate that sampling distribution reasonably well using the appropriate normal distribution. So remember that according to the normal approximation to the binomial distribution, which again is an application of the central limit theorem, it says that for sufficiently large n, the binomial distribution with n trials and success probability p can be approximated by a normal distribution that has the same mean and variance as that binomial. So the normal distribution that we're talking about would have a mean equal to n times p, which is the mean of this binomial, and a variance equal to n times p times 1 minus p. which is the variance of this binomial distribution. And obviously, if the variance is n times p times 1 minus p, then the standard deviation, which is just the square root of the variance, would be equal to the square root of n times p times 1 minus p. So if the sample size is large enough, whatever that means, then this binomial distribution, if we think about the graph of a binomial distribution, and then think about superimposing on the top of that a graph of a normal distribution that's centered at the same place, it's got the same mean, it has the same amount of variation, so it's got about the same amount of spread, right? Then we ought to be able to approximate areas under the binomial graph with corresponding areas under the normal distribution curve. That's the idea behind normal approximation to the binomial distribution, and it's the idea behind this approximation that we're going to be looking at in this lecture. All right, so as we've said, that under the null hypothesis, the test statistic x tot has a binomial distribution, specifically with success probability equal to 0.5. X tot always has a binomial distribution, regardless of whether the null hypothesis is true. But if the null hypothesis is true, and in particular if that boundary condition is true, we can go even further and say that the success probability is 0.5. And that's very specific and important information that we need. In that situation, the mean of that distribution, the expected value of x tot, is n times p, which is n times 0.5, or n over 2. And the variance of x tot, n times p times 1 minus p, is n times 0.5 times 0.5, or n over 4. And if the variance is n over 4, then the standard deviation is the square root of n all over 2. So by the central limit theorem, for sufficiently large sample sizes n, x tot will be approximately normally distributed. And notice that I have a dot on my is distributed tilde there. That means is approximately distributed as. So we know that if the null hypothesis is true, the exact distribution of x tot is this binomial distribution with n trials and success probability p equal to 0.5. But for large enough sample sizes, that exact sampling distribution can be approximated by this normal distribution. And in particular, we can use the normal distribution in those cases to very easily compute probabilities, such as computing a p-value or finding percentage points of that distribution so that we could use that to find critical points. So if x tot is approximately normally distributed, then if we standardize x tot by subtracting off the mean of its sampling distribution and then dividing that difference by its standard error, then that standardized version of x tot will be approximately standard normal. And so what we're going to do is call the standardized version of x tot cap z sub c for a calculated test statistic that is a standardized test statistic. And so what this result tells us is that z-calc will be approximately standard normal. And hence the standardized version of x tot, which is z-calc, can be used as the test statistic in approximate large sample hypothesis test about the population median. And so instead of performing the test using x tot along with its exact sampling distribution, the binomial distribution, which as we've seen is a bit cumbersome to use, isn't it? You have to have the calculator with that functionality built in, or you have to use a spreadsheet. For example, Microsoft Excel spreadsheet has the binomial PMF and it's got the binomial CDF built in. And so you can use spreadsheets, but in the absence of that, we can do an approximate test using a normal distribution. So instead of using x tot along with its exact sampling distribution, which is the binomial, we can use z-calc as the test statistic and then use the standard normal distribution as the approximate reference distribution. Let's put all this together. So if we wanted to perform a two-tailed test where the null hypothesis says that the median of the population is equal to some specified value cap m sub 0 against the alternative, which would then be that the population median is not equal to cap m sub 0, then we would have a two-tailed test. The rejection criteria specified in terms of the test statistic and critical point. This should look very, very familiar for you because this is the same kind of rejection criteria that we've used whenever we're using a standard normal distribution as the reference distribution. We're going to reject the null hypothesis if zcalc is less than negative z sub alpha over 2, or if zcalc is greater than positive z sub alpha over 2. Now, what is alpha? Well, again, alpha is the significance level. Now, we do have to keep in mind that zcalc in this context is different than zcalc in the context where we're testing hypotheses about a population mean. In this context, zcalc is calculated as 2 times x tot minus the sample size all over the square root of the sample size. And then to calculate a p-value for this test, the p-value is going to be equal to 2 times the probability that z, where z is a standard normal random variable, is greater than or equal to the absolute value of little z sub c, where little z sub c is the observed value of the test statistic cap z sub z. If we want to perform a left-tailed test where we're trying to show that cap m is less than some specified value, then we would have this left-tailed test. So the null hypothesis is that the population median is greater than or equal to the specified value against the alternative that says that the population median is less than the specified value. And so the rejection criteria at a significance level of alpha would be to reject the null hypothesis if zcalc, which again is twice x tot minus n over the square root of n, if that value is less than negative z sub alpha. The p-value formula for this test is given by the probability that the standard normal random variable z is less than or equal to the observed value of zcalc. And by the way, where would we get these probabilities? Well, we would get them from the standard normal table. And then finally, the right-tail test. In this situation, we're trying to show that the population median is greater than some specified value, and so that goes in the alternative. Or the opposite of that would go in the null, so the null hypothesis would be that the population median is no more than the specified value. All right, and then the rejection criteria at a significance level of alpha would be to reject the null hypothesis if zcalc is greater than z sub alpha. The p-value would be the probability that the standard normal random variable is greater than or equal to the observed value. And again, we would get that from the standard normal table. So let's put this all together. And so I've got this information consolidated here on a few more slides. So in testing hypotheses about a population median using this large sample approach, right, where we are approximating the sampling distribution of x tot using a normal distribution, and we've got our 3 types of tests that we can perform: a two-tailed test, a left-tailed test, and a right-tailed test. For each of those 3 tests, we have our rejection criteria. So for the two-tailed test, we're going to reject the null hypothesis if zcalc is either less than negative z sub alpha over 2, or if it's greater than positive z sub alpha over 2. For the left-tailed test, we reject for small values of the test statistic. In particular, if zcalc is less than negative z sub alpha. And then for a right-tailed test, we reject for large value, in particular, if zcalc is greater than z sub alpha. And again, remember that in all 3 of these, zcalc is 2 times x tot minus n over the square root of n. And finally, to calculate p-values, if we've got a two-tailed test, then the p-value for the test, and again, these are approximate p-values, right? Because we're using an approximation to the true sampling distribution of x tot. So I just want to point out here that the p-values that we obtain using this method right here are not going to be exactly equal to the true p-values that we would get using the binomial distribution, because the reference distribution that we're using is an approximation to that binomial distribution. Okay, using this approximate technique, these approximate tests, for a two-tailed test, the p-value is 2 times the probability that a standard normal random variable is greater than or equal to the absolute value of the observed value of zcalc. For the left-tailed test, the p-value is the probability that the standard normal random variable z is less than or equal to the observed value of zcalc. And then for a right-tailed test, the p-value is the probability that a standard normal random variable is greater than or equal to the observed value, Z sub C. Okay, so that wraps up the development of this procedure. I'll stop the video here and create another video that's got some examples. So I'll see you in the next video.